Thank you, Aaron. Good morning. So what I'm going to do is talk about a business model that we believe we've created, and we've created that by going through the development of our first product, which is currently using an MIT scale, TRL level 7. So it's not ready, but it's ready for doing prototyping. And we call that business model Autonomous Vehicles as a Service. So what is AVAS? Basically what we want to do is remove humans from operating vehicles in certain applications. So we want to deploy teams of unmanned vehicles to replace human-operated vehicles. There's still going to be a human involved because you can't have a whole bunch of unmanned vehicles running around doing things without someone being in control. So there's a human supervisor who's able to observe what the vehicles do, but can also take control if required. And these vehicles, we don't lock ourselves into a specific kind of domain. I've put up 4 different kinds of domains there, which is a term we use. So we will be able to handle unmanned ground vehicles, which is basically an autonomous vehicle car. UAVs, which you know about, are also called drones. A USV is a ship or a boat. It goes on water. A UUV goes underneath the water. And in general, this is the type of architecture that we anticipate putting together. So I'm going to talk about some of the problems that we've encountered and how this architecture can be put together, and even show you at the end a pilot project that we're looking at. So there's not enough time, so I'm going to focus on the business case, the security, what we call human-robot collaboration, sensors, and AI. And take a step backwards. So our first product is going to be in the perimeter security business. And if you look on the far left-hand side of this diagram, that's a legend of a machine called Talos. And Talos was supposed to protect a woman called Europa, which is where the word Europe comes from. And a Talos is effectively a physical security robot. So mankind has basically been waiting for this technology to come now for 2,500 years. And still not 100% there. And then you look at 1936, Westinghouse built a robot we called Electro. It had no real specific purpose. It didn't go anywhere. And one of the important use cases the engineers decided to implement was that it could smoke a cigarette. So it could walk, it could talk by playing recordings, and it could smoke a cigarette. So it obviously couldn't go anywhere. Honda spent a lot of money from about 2007 to 2014 on the Asimo. And the Asimo could run, it could jump, it could climb stairs, it could lift basic weights, and it could communicate. But it really didn't have a well-defined business model. So it's not sure where that's going to go yet. And now you see in 2017, there's a company whose name I forget right now, it could be PAL, has invented a robot called Talos. So we've come full circle. And Talos, I think, has the ability to lift heavy items like we saw in the previous presentation. But the important thing is that if you don't create the business model, then essentially you create an experiment. So Asimo is an experiment which was probably around $80 million. I don't know how much Electro cost. So when you look at, this is an old slide, it's 2016, and you look at a business model, everyone was really excited about drone delivery. Well, that was the cost in 2016. It couldn't really compete. I don't know how that's changed, but I still think that's an issue. I still think part of the issue is, what are you actually delivering? Because a drone can't lift a lot of mass. In Canada, we just passed regulations, and if you buy a drone, that drone can't exceed a height of 100 meters in flight and can't be a total mass of more than 500 grams. That's not very much. So until we can get the regulations in place, the business model isn't going to work very well in a country such as Canada. So we heard this morning that technology is moving at a very rapid pace. Well, in robotics, I don't think that's necessarily the case. But the good thing about robotics is we rely on technology from a lot of different sources because it's a complex problem and we have to deal with a lot of issues. And a lot of that technology is now coming to place in the last 10 years. So that's why we're seeing a lot of improvements and things like drones that deliver empty boxes. So this is just an example, a different example of what's called Moore's Law, which we know where processors were doubling in performance every year. Well, in 1924, a Russian physicist invented the LED. And the LED is actually that little switchy-looking thing in the top right-hand side. It glowed green. Nobody knew what this was for, nor had a purpose for it. But until we got semiconductors working, starting with in the early 1940s and the 50s, we still didn't have a use. But you can look at, since 1962, the power of the LED has doubled every 36 months, just like memory has gotten denser. So it's Moore's law done differently. But now we can buy LEDs for as little as pennies, or a peso, I guess. And we're now using LEDs in our homes. There's LEDs right there, those blue lights. So it's a technology that's really changed, but it took a long time. So we mentioned before you need good business cases. Here are two very successful business cases. So one on the left is everyone's familiar with, that's the Roomba. And on the right, there's manufacturing. Robot sticks on the floor, does the same thing over and over again. And Roomba is about 10 years ago. Manufacturing's been at least 60 years. And here's two more recent business cases, and this is getting closer to where we want to go with our technology. These are two mining trucks that they're Caterpillars, and they're used to do open pit mining in at least two mines in Australia. They're unmanned. And the purpose of that truck is to go to a place, it gets loaded up with ore, and then it climbs out of the mine. And an open pit mine is very big, so it's got a big conical path that it climbs up. It goes to another place and drops the ore. So it's somewhat autonomous. It's basically given a path that it repeats over and over again. Someone has to tell it where to start and where to end. So essentially, the unmanned operation is there. It's there to increase productivity. One of the problems is that it's not really unmanned because what doesn't show in the pictures is a little truck that has to go up and down this road more than once a day looking for rocks. And a rock this big, if that truck rolls over it, it will damage the tire. So then you have another problem you have to solve. But at least they'll solve that eventually. Maybe they can use a sensor to detect something that size and the truck can avoid it. The bottom right-hand side is getting closer to where we want to go. So this is the port of Rotterdam. And in Rotterdam, they use automated vehicles to transport the containers. So that increases the ability to unload and unload ships. Now, these aren't automatic guided vehicles that you would see in a factory that basically follow a pattern on the floor. These vehicles can go anywhere they want. And they actually will negotiate with the other vehicles on the port to make sure that no one's running into each other and they get their containers moved from point A to point B very quickly. So that uses a form of AI that we will use in our products. Examples of unsuccessful business case. So this is actually from our own company. We developed this robot in about 2007. We built 300, and we didn't really know what it was going to be for. We thought it would be an indoor security robot, but didn't know anything about indoor security. It had one sensor, a proximity sensor, and I said we built 300. We sold 290 to universities, and they got the robot, threw all the plastic away, and used it as an experimental tool for research. We only sold 4 to security companies because no one really understood what we were trying to do. We didn't convey the model properly, and we even named it incorrectly, and we priced it incorrectly. And so, bottom picture, it's not a very good picture. It shows 2 kids hugging one of these robots. That's actually was a common occurrence. We take a robot, we go to like a museum or a trade show, and if there was a small kid there, they would run up to it and they would hug it and kiss it, and some kids actually lick it. And so it wasn't a very successful security robot. There's a university in Ohio bought one to use it as a mascot. It's a mascot for their STEM program. And so it actually has an honorary degree in computer science. So it's the only robot in the world to graduate from a university. Kind of. Anyways, so sensors. What we've found out is basically you need lots of sensors on the types of vehicles that we're developing. And here's an example of how a sensor can fail. So this is an early project we did. It's actually an analog, the term is analog lunar Mars rover. So analog means it goes to a place that looks like the Mars or looks like the moon. This one will never go to space. In northern Canada, there's an island called Axel Heiberg, and it looks like Mars, and it feels like Mars if you go there. It's very cold. So it can the purpose of it is to do autonomous surveying and mining. So in theory, You go to the moon, another robot plops this on the ground. It says, go to this location, map it out, take samples, come back. So we're testing this in Canada. One of our assumptions is, well, it's the moon. It has a pretty benign environment. No GPS, but we can deal with that. And we're 2 o'clock in the morning, one night. We're doing nighttime studies. The robot is probably at the end of this room. It has a little light on it so we can see it because it's so dark. It's a red light. It's flashing. And the robot isn't coming towards us. It's actually going this way. And the robot's saying, there's an object in front of me. And we're thinking, well, what could that be? Could it be a coyote or could it be a deer? And turns out it's bugs. The bugs are attracted by the light, and we're just using a LiDAR for perception. The LiDAR is bouncing off all these little bugs, and it looks like a solid object. So with software, we can fix that problem. Here's another example of a sensor that failed. Gas plant I worked at a while ago. The staff wanted to go home early. They decided to put cold air over top of a hot sulfur. And that caused a fire. Because you put air over top of hot sulfur, it's an exothermic reaction. If the system, which was a computer-based system, could say, Dave, are you sure you want to put cold air over the hot sulfur and cause a fire? And Dave could say no, and he'd be able to continue working for a bit and maintain his job, which unfortunately the manager failed. So another example, I'm running out of time quickly here. So in 2003, we had a big power failure in northeastern North America. That problem could have been saved if there was some sort of system that would tell the operator something was going wrong. All the data was there, but no one was paying attention. So about 1 o'clock in the afternoon, failures were occurring in Ohio and New York. And it was caused by basically people overusing their air conditioners. And these failures caused transmission lines to fail. They caused relays to pop, and they caused transformers to blow up. So eventually someone at a nuclear power station in Ontario says, I think there's a problem, and decides to bring all the guys in from the hallway to say, we have a problem, what is it? And what they should have done is start spinning down all the nuclear reactors. You can't do that instantaneously, it takes time. Unfortunately, you couldn't do it fast enough, so 10 million people lost power. So that's the evening in downtown Toronto on August 14th, 2003. Looks very romantic, but there's no lights. Here's another example. I'm going to skip this one. It's running out of time. So we're trying to deliver a product that we can put into outside airports or along borders. And what we want to do is ship the product from the factory and say it's virus-free, but then have the product actually monitor itself continuously saying, I have a virus. Now, we want to do that because this statistic is real. Basically, since this morning started, 2 viruses have been created that can intrude into an autonomous vehicle. And what we want to do is not try to say it's virus-free. We want to be able to say, we have a virus in the vehicle, let's remove it from service and fix it, rather than continue operating. And there's an example of autonomous vehicles, how they can be attacked. We'll skip ahead. So human-robot collaboration. This shows robots playing soccer. This is one of the Japanese Grand Challenge problems for 2050. And the way those robots are looking at that ball at the bottom, I don't think CONCACAF has to be worried about any threats soon. But it shows collaboration because you have 2 teams competing. The teams have a mission. The mission is to move the ball down the field and score. The robots can be autonomous and they can collaborate with each other, but there's still a manager. The manager is a human manager, and he's making decisions. He's deciding whether he should remove a robot off the team and put a different robot in with different capabilities, or change the type of tactics that the robots are doing. He can do that, and the robots will dynamically change. So this is what we're trying to do with our vehicles, and we call that human-robot collaboration. The other problem is, and this is a research area, there's lots of robots on the field. Can one human actually deal with 10 robots in terms of understanding the information? So there's a human cognitive problem that no one knows about yet. So we have an experiment, which is the last slide I'll go through, but this is our experiment running right now, and it's an experiment into human-robot collaboration, and we created a simulation. In this simulation, we have birds flying around an airport. And the things that look like crosses are drones, and the drones detect the birds and try to shoo them away. And there's roughly 4 drones in that picture. Actually, there's only 3. And the user interface is going to see something like this. It's like a GIS image of this map. And you'd be able to get telemetry from the robots, and you'd be able to control the robots or make them do something. For example, the robot on the bottom left-hand side is just sitting spinning. But there's a threat to his bottom right. That little red triangle is the bird threat. That robot that's spinning can't see anything. So maybe the human could say, well, change position. And then we can deal with the threat properly because that robot is on the approach of the runway. Can I do one more slide? Okay, so this is the last slide. And these are the areas that we're looking at for when we take our product to the market and actually start commercializing. We're looking at 3D manufacturing, what's called generative design, which is iterating the 3D part and try to remove material so you can save weight and cost, but maintain the same strength. 5G is what we need to support our products. Our typical robot could, worst case, generate 5 terabytes of data a month. So we need a communications network that can transport that data. The slide I skipped was about trusted AI. That's basically getting information from your decision-making system and deciding if you want to believe it or not. That's all a current research topic. And then some of the use cases we're looking at are delivery still, physical security, first and last mile, and precision agriculture. And then all of our autonomous vehicles will be electric. That's probably one of the things that has to be solved before general purpose electric cars are going to be available. Okay. Start. Last slide.